Hello and welcome to the second video on the Reigate Maths series on graphs from the first year of the decision topic for the further maths specification. My name's Simon and in this video we're going to be looking at a lot of terminology to do with graph theory and some of the specific maths to do with it as opposed to a overview. If you haven't watched the introduction video on graphs, I would strongly advise you do that because it's going to introduce to you the types of graphs that we're going to be looking at in this video and going forward. So we've got this graph here made up of the vertices A through to H, and I've listed a couple of terminology or terms here that we're going to be talking about. The first is the vertex set, and this is the set of all vertices in the graph. Now, because it's a set, we use the set notation, so the curly bracket, and then we just list the vertices in the graph. And this is the vertex set of this graph. The edge set is going to be the set of all of the edges in the graph, which is going to be a much bigger set, because we've got the edge AB, the edge AC, AD, and so on. I'm not going to write out the whole set, but you can see the idea here. So the vertex set is the list of all the vertices in the graph. The edge set is the list of all the edges in the graph. A couple of other key terms here is the idea of a subgraph. This is a graph whose edges and vertices are also in the graph. So we could have the graph that looks like this with A, B, C, and D. Because all of these vertices and the edges of this graph are also in the main graph, this is a subgraph. If we had, for instance, A, C, B, and E, and we had some vertices like this and some arcs like that, this is a subgraph. This is not, because this arc A to C is not in the original, A to E is not in the original graph. We can see there's no arc on the original graph that directly joins A to E. So this first one's a subgraph, this one isn't. Now, a really important concept is the degree of a vertex. And the degree is the number of arcs that are touching the vertex, or known as incident to it. So we can see here we've got 3 connections at A. So A has order 3, and so on. B has order 3, C has order 4, D has order 5, and so does E. F has order 4, and then G and H both have order 3. If a vertex has even order, then it just means the order is an even number. So in this graph, C and F are the even vertices. The odd vertices are then A, B, D, E, G, and H. This concept is really important for an algorithm that's going to come up in a later video called root inspection. The order is as simple as that. It is the number of arcs incident to it. Now, sometimes a little bit difficult is we will have something like this. This is called a loop. The order of this vertex is 3. Because although there are only 2 arcs connected to it, we have 1, 2, 3 direct connections to this vertex. Okay, so although it doesn't necessarily look like it, this vertex is an odd vertex as well. So far we've looked at specific properties and names of things in the graph. Now what we're going to do is talk about some of the terminology for motion about the graph. And these terms are really important that they are distinct. So a walk is the most general version of these. It is a route through the graph along edges from one vertex to the next. So a walk could be A, B, C, B. That is a walk. We are moving around the graph. A path is a walk where no vertex is visited more than once. So this walk is not a path because we visited B twice. So a path could be A, B, C. That is a path. We move from A to B to C, and we repeat no vertex more than once. A trail is a walk where no edge is traversed more than once. So again, this ABC is a trail as well as a path. But ABCA, that is also a trail, but not a path. Remember, path, we visit each vertex exactly once. Trail, we go over each arc exactly once, or no more than once. So we go across AB, BC, and then CA. This is a trail. Two vertices are known as connected if there is a path between the two vertices. So in this graph here, there is a path or a walk between every single pair of vertices. We then therefore say that the entire graph is connected. But we might have another graph that looks like this, with three vertices here, A, B, and C, and then D and E over here. Something like this. This is a whole graph, even though it's in 2 bits. This is not connected because B is not connected to E. There is no path that joins B to E, so this graph here is not connected. If we did this, it then becomes a connected graph. Now, even though on this graph here, F and A are not directly connected to each other by a single arc, you can walk from A to F in a bunch of different ways. The number of arcs it takes does not matter for connectivity. Okay, it's just if you can walk from one to another, then they are connected. We've already seen this already, but this here is called a loop. When we have one arc that starts and finishes at the same vertex. And this, if we have 2 vertices joined by more than one arc, we refer to this as having multiple edges. A graph is known as simple if there are no loops or multiple edges. So this graph here that we've been talking about is simple. There are no loops and no multiple edges. If we did this, connecting F to G by another arc, that's no longer simple. If we put arrows on a graph to denote direction, So we can, on this graph here, we could now only go from F to G, not G directly to F. We sometimes refer to this as a digraph or directed graph. The last sort of terminology before we start looking at some examples is known as Euler's handshaking lemma. And this is quite useful for sort of broad graph theory. And it's for any undirected graph, so not a digraph, is the sum of all the degrees of all of the vertices is 2 times the number of arcs, which should make sense because each arc starts and finishes at one point. So one arc contributes 2 to the total number of degrees. Okay, which then results in quite an important property that there have to be an even number of odd vertices, which is a really useful property again when we start to look at some of the algorithms on graphs. So we're going to move away from kind of this terminology and start looking at some examples of using it. So this is a very useful example to kind of address quite a lot of those properties specifically to do with simple graphs. So here we have a simple graph with 5 vertices, and it has degrees x, x plus 1, x plus 1, x plus 2, and x plus 3. So vertex 1 has x, a degree of x, vertex 2 has a degree of x plus 1, and so on. And we want to show that in this case, x must be odd. Now this comes from Euler's handshaking lemma. So we know the sum of degrees is equal to 2 times the number of arcs. Now we don't know the number of arcs, but we know it's 2 times something. So therefore the sum of the degrees must be an even number because it's 2 times something. So let's look at the sum of the degrees. We've got x plus 1 plus x plus 1 plus x plus 2 plus x plus 3. Okay, we add those all together and you get 5x plus 7. And we now need to explain why x must be odd for this to be even. Well, we know that if x is even, then 5x is even, so therefore 5x plus 7, even plus an odd, is odd. We know that this is not possible because we know the sum of the degrees must be even. So 5x plus 7 cannot be odd. Because we've said if x is even, this must be odd, this can't be odd, so therefore x can't be even. So therefore x must be odd. Now finding the value of x, it refers to, we know the fact that it's a simple graph. So for a simple graph, we know the maximum degree, because there's 5 vertices, the maximum degree of any of the arcs, any of the vertices must be n minus 1. So in this case is 4. So we know that x plus 3 must equal 4 because x has to be a positive number. because you can't have something with degree. Well, you can have something with degree 0, but then this doesn't work. So but regardless, this is the biggest vertex, or the vertex with the largest degree. So therefore, x must be 1. So we know that this simple graph now has one vertex with degree 1, 2 vertices with degree 2, 1 vertex with degree 3, and 1 vertex with degree 4. So if we wanted to, we could then draw that. Looking now at some further properties, this is a different simple graph. So still simple, which is important, has 10 vertices. We want to state the minimum and maximum possible degree of a vertex. Okay. So the minimum the minimum degree can be 0. And the maximum degree, as we've already seen, is n minus 1. So we could have a vertex with no arcs on it. And something that looks like this, and then obviously more vertices there. This is still a graph, it's just not a particularly interesting one. Now the reason here we know x can't be 0 for this example is x must be odd. We've already proved that. 0 is an even number. So show that the degrees of the vertices cannot all be different in this case. So we're proving that at least 2 vertices must have the same degree. We don't know what that degree is, but it has to be the same for at least 2 vertices. So let's use a similar logic here, where we said, if something is true, prove that it doesn't work. So therefore it can't be true. So let's think if they are all different. Okay, then the degrees must be unique, so 0, 1, 2, and then all the way up to 9. So we have 10 vertices, all of the degrees must be different. We know it's simple, so the maximum degree has to be 9. So the degrees must have each one of these numbers. So we can now discuss this in either 2 ways. We can work out the sum of the degrees, which is 45. Half n plus 1, is the sum of numbers from 1 to 9, which is odd, and we've already seen the sum of the degrees must be even. Okay, so the degrees cannot all be different. Or we can think, well, if we have one vertex of degree 9, that must be connecting to every other vertex. But we have the vertex of degree 0 connects to no other vertex. These 2 properties can't happen at the same time. We can't have one vertex connecting to everything and one vertex connecting to nothing. Those contradict each other. So again, therefore, at least 2 of the vertices must have the same order. Thinking about simple graphs is really, really useful in kind of the broad graph theory sense, because it can really quickly tell you whether a graph works or not. There are going to be some specific types of simple graphs that we're going to look at in the next video, but this is kind of a long video just to go through some of the terminology and important points about graph theory. Thank you for watching.